In this lecture, let us discuss a little bit about hypersonic flow and on shock tube. In the previous lecture, we had just started discussing hypersonic flow in the context of very high free stream Mach numbers, and we said that usually it is higher than 5, but that is just a ballpark number. It should not be taken as a sacrosanct boundary between supersonic and hypersonic flow. The main issue is that there are certain significant changes which come up in the flow field characteristics, which distinguishes hypersonic flow from supersonic flow, and we need to understand them in a more methodical manner, and that is how we need to distinguish between the two regimes. Incidentally, the transonic flow that we saw around Mach 1, slightly lower and slightly above Mach 1, as well as hypersonic flow, they both have a common characteristic. Though incidentally, the free stream Mach number range, it is slightly on the lower side for the transonic flow, while here it is much higher than 1. They have a common nature in the sense of nonlinearity. What do we mean by that? If we look at it from the mathematical perspective, if we looked at the governing equations, then you will be able to appreciate this better, in the sense that when we look at these two flow regimes and you try to discuss the governing equations from the point of view of small disturbances or small perturbations, you find that the governing equations can never be linearized. This gives the nonlinear nature from a mathematical perspective. If you recall that in the subsonic regime or in the supersonic regime, when you talk about small disturbance or small perturbation flows, that means very small changes happen within the flow field because of presence of a body, then the governing equations can be linearized in these two regimes. For subsonic flows, for example, you have seen that under certain assumptions, the governing equation is Laplace equation, which is a linear partial differential equation, for example. Then in supersonic flow, we had discussed about velocity potential equation. If that equation is treated from the point of view of small disturbances, we can also show that the velocity potential equation will become a linear partial differential equation, which is left as a homework for you. But such simplifications never occur for transonic or hypersonic flow. So, from a mathematical perspective, we therefore have an answer why the nonlinearity. And now, that nonlinearity in the mathematical behavior should also show up in the aerodynamic characteristics. The characteristics in general should show complex behavior. So, let us get into the hypersonic flow behavior and try to discuss it more from a physical perspective now. So, these flows they are found to occur on reusable space shuttles during atmospheric re-entry, on long range ballistic missiles used in defense applications when they fly through the outer extent of the atmosphere at very high speeds, and also on rockets at high altitudes. When rockets are ascending through the atmosphere and they are accelerating significantly to high Mach numbers, you see hypersonic flow occurring. what are the flow characteristics which change significantly as the Mach number becomes large. So, these are the points which are of main interest here, which sets it apart from the regular supersonic regime. Shock waves are formed closer to the body. This we had discussed earlier also in the previous lecture. Therefore, the thin flow region formed between the shock and the body surface is called as a thin shock layer. Viscous dissipation within this layer is very large at hypersonic speed, which leads to excessive heating of the flow. What exactly happens? You have the body surface exposed to a very high Mach number, and then because of the viscous effects there is going to be a boundary layer anyway, a hydrodynamic or velocity boundary layer, which will slow down the flow from such a very high velocity just beyond the boundary layer to 0 velocity on the wall, and that is happening over a very small length scale. What happens as a consequence is that the velocity gradients become enormously large, and that leads to a lot of heat dissipation, because the layers of fluid are rubbing against each other very aggressively, and that is what releases a lot of heat, and that raises the internal energy of the air. What happens as a consequence? The temperature will go up significantly. You have to look at the thermal boundary layer as well. It is not enough to look at the velocity boundary layer. You will find that there is a sharp spike in the temperature compared to what you have in the free stream. This is the thermal effect of such a high speed flow coming in contact with the solid surface, and the enormous amount of viscous dissipation which is happening due to the large velocity gradients is the reason behind this sharp rise in temperature. All three modes of heat transfer would be active in this case: radiative, convective and conductive. Temperatures are so high that radiative heat transfer also becomes very important, and sometimes the temperature in the flow as well as on the wall can reach very high levels. You have to keep the wall cooler, otherwise it will damage the vehicle. So, the wall has to be protected by a heat shield which is ablative in nature. That means that heat shield will try to melt and evaporate from the surface, taking away a lot of heat from the surface and therefore keeping it cool. So, these kind of methods are followed in order to save the vehicle from the excessive heating. Due to enormous heating as well as the high altitudes where these flows usually occur, because the vehicles are in a thinner part of the atmosphere at much higher altitudes. This is where hypersonic flows usually are noticed in practical applications. The densities are much reduced compared to sea level conditions, and what happens is the boundary layer thickens up. Once the boundary layer thickness increases, the displacement effect of the boundary layer is also larger, and it affects the outer inviscid flow. The inviscid flow gets displaced further, and that changes the pressure distribution on the body. If that change in pressure distribution occurs on the body, it affects the forces and moments which act on the body, and it can have a serious issue with the stability of the vehicle. So, we have started looking at different effects. We continue to discuss that. The flow can become chemically reacting. We said earlier that the gas can ionize at such Mach numbers, and thermodynamic characteristics may be altered significantly. The calorically perfect gas assumption, that means Cp, Cv are constants, would not work at those conditions. And though it works for lower Mach number supersonic flows, they would not work at these Mach numbers, and both of those specific heats, they become functions of pressure and temperature in hypersonic conditions. You could dig a little deeper into kinetic theory of gases. and try to get an answer to these questions, why it happens at higher temperatures. Complex chemical reactions occur at the body surface if it is coated with an ablative layer for cooling purposes, which often is the case. So, there will become complex chemical reactions. It is not only that the air is getting ionized, but the materials forming the ablative layer, they are also reacting. So, the chemical reactions become very complex. Since the flow is at a high velocity, the fluid particle in the free stream crosses the vehicle length within a very short time. If chemical reactions get completed within this short transit time, then we have equilibrium chemical reactions, but if not, then non-equilibrium chemical reactions would have to be accounted. And the non-equilibrium nature of chemical reactions can alter the flow characteristics further. Therefore, even analyzing hypersonic flows is that much more complicated. Very often you will see that these vehicles have a blunt nose. Unlike the sharp wedges that we were discussing at supersonic speeds, you would very often see blunt noses being used at much higher Mach numbers. The question is why? You would have, of course, a detached shock, which is a bow shock, which will obviously create very high wave drag. How does it help? There is a so called a shock standoff distance. That means the distance between the wave and the nose part of the body, and the shock is purposely formed away from the body surface. Why? Because the enormous heat formation across the shock wave at those very high Mach numbers is largely carried away by the flow, and a much lesser amount of heat would reach the surface, and that is a desirable feature. So, if you keep the shock away from the body, then it is beneficial in the sense that it heats the body less. Due to the highly curved bow shock, the shock angle changes from point to point. So, you can figure out that if you try to work out the beta, the wave angle, it will be different at different parts of the shock wave. That is a typical feature of a bow shock. So, there are varying entropy levels. If you follow streamlines which are crossing this wave at different points, it goes through varying entropy changes, and we can show from the energy equation that produces vorticity in the flow behind the shock. You can try to explore a law which is called as Crocco's law in this respect. If there is additional vorticity which is created behind the shock, remember it is inviscid flow that we are talking about. So, it is a mechanism of generation of vorticity in an inviscid flow. In a real flow, there is also vorticity in the boundary layer, and this vorticity which is created by an inviscid mechanism can interact strongly with the boundary layer and alter its characteristics. Well, we looked at quite a few interesting features of hypersonic flow. Let us also look at some numbers. So, what we are going to do is, we are going to take some equations which we developed earlier for supersonic flows, and we are going to just bluntly impose the Mach number tending to infinity limit and see what happens. So, when we look at the exact normal shock relations for supersonic flow, in that we are just posing the condition that m1 tends to infinity, and then what do we get? The downstream Mach number behind a normal shock, which is occurring with infinitely large upstream Mach number, is 0.378. We are still assuming gamma to be 1.4, which is of course a questionable approximation, but for simplicity we have done that. Why is it a questionable approximation? We already said that Cp, Cv cannot be considered to be constants. They are going to be a function of pressure and temperature, and therefore, they would change from 1.4, they would not remain this way. You would find that when the Mach number grows larger, the temperatures are increasing significantly, the gamma tends to reduce. It may get closer to 1.3, 1.2 of that order. What about density ratio? that too saturates to a finite number 6. That means, the density across the shock is 6 times that of the upstream. There are other relations where the limiting condition will give you infinitely large ratios. We are not discussing all that here. We pick up the theta beta m relation which we had for oblique shock wave, and again assuming gamma 1.4 and theta to be small, we can show that beta is 1.2 times theta. That means, the wave angle is just 20% larger than the compression angle. What does it convey to us? It again conveys and re-emphasizes the concept that the thin shock layer is produced in hypersonic speeds. So, we therefore discussed quite a few interesting features of hypersonic flow. Now, let us discuss a bit about an experimental apparatus or instrument which is of enormous use for exploring hypersonic flows. But of course, it is not only confined to hypersonic flow studies, it is also used for supersonic flows. Additionally, there are also wind tunnels, shock tunnels which are dedicated for hypersonic flow studies as well as for supersonic studies, which we will look at later in the course. So, shock tubes are useful instruments for conducting gas dynamic studies, and they find important applications in the study of high temperature gases, and we already understand why high temperatures occur in hypersonic studies. And in this device, unsteady wave motion is studied. What is the characteristic of this apparatus? It looks comparatively simple. It is a long metallic tube closed at both ends, and there is a diaphragm separating a region of high pressure gas from a region of low pressure gas. The gases in the two regions can be different. They can be even maintained at different temperatures, and if they are different gases, they would also have different molecular weights. Then there is a point when the diaphragm is ruptured or broken, and once it is broken, then what happens is the two gases can interact with each other. The diaphragm can be broken either by using some electrical current or some mechanical means, and once it breaks, what happens is the high pressure section, which is called as a driver section, the gas from that section rushes into the other section which is at a comparatively lower pressure, which is called as the driven section. A shock wave from the driver section moves into the driven section, and simultaneously an expansion wave propagates into the high pressure section from the driven section side. Now, before we proceed further, it may be a good time to draw a sketch of a shock tube. As I said, that construction wise it looks pretty simple, but that should not be distracting us in the sense that there are a lot of accompanying complexities in its design and in its instrumentation. So, this is, let us say, the driver section, this is the driven section, and we said that there could be two different gases, but the most important thing to understand is that the driver section gas is at a much higher pressure than the driven section gas. So, let us say if you are making a pressure plot, then the pressure plot would look like this, and then this is before diaphragm rupture. Right. So, what happens when the diaphragm ruptures? If we are looking at the flow after few instants, then how would the flow look like? Let us try to draw it. So, we are looking at the flow. After a while, by then the diaphragm has ruptured, and what are we seeing? We are seeing a normal shock moving towards the driven section, and simultaneously we are seeing expansion fan moving towards the driver section. There is another interesting entity here which is called as a contact surface. The flow behind the normal shock gets dragged. You have an induced motion which is produced behind the moving normal shock. So, we will discuss once again when we look at the slides where we have a write up on all this. We will try to mark it appropriately, so that you can see the variations, how they are occurring. So, that is how it is. So, what do you notice? As the shock is moving into the driven section, there is a large pressure jump across the shock here. There is a gradual pressure change across the expansion fan. There is no sudden change. Why? Because the expansion fan is accompanied by an isentropic change, and therefore, the property variations are smooth. So, this is how the flow will look like a few milliseconds, let us say, after the diaphragm has ruptured, and then ultimately if you look at it after some more time, the shock would have reached this end of the shock tube, and then it reflects back, it returns back. The expansion fan would have reached the other end of the shock tube, and it also reflects back as an expansion fan. Remember here that the waves are reaching solid walls and they are reflecting back, and therefore, they reflect back in the same manner. A shock reflects back as a shock, an expansion fan reflects back as an expansion fan. We go back to the write up again. Now that we have seen the pictures, we will recall that as the normal shock propagates, it increases the pressure of the gas behind it and induces a mass motion. The interface between the driver and driven gas is a contact surface. That is an interesting entity. Across it, the entropy can change discontinuously, but such a layer cannot sustain changes in pressure or velocity. So, pressure and velocity jumps are not sustained. It is only entropy which can change abruptly across a surface like that. You can also explore a term called slipstream in your spare time as a homework, that what this means and whether that has a connection with contact surface. Eventually, the normal shock reaches the end of the shock tube and it reflects back. We discussed about this too, and we also discussed how shock reflection occurs from a solid boundary. Earlier, in the context of shock wave boundary layer interaction, we had discussed that how a compression wave reflects back from a constant pressure region as an expansion fan. So, that was an opposite nature. Let us look at the next point. The expansion wave propagates to the left smoothly and continuously, decreasing the pressure to the lower value behind it. This is an isentropic region, and eventually the expansion wave reaches the end of the shock tube and reflects back as an expansion fan, just for the sake of completeness. We are mentioning that. Now comes a very important point. which is very important for the designers of shock tubes and users. We need to understand that speed of sound in a light gas is faster than in a heavy gas. Try to figure out again why this happens. I leave it as a homework for you. You already know a lot about sound wave propagation, so you should be able to figure out now. So, having accepted this fact, we make a statement that to maximize the incident shock strength for a given diaphragm pressure ratio, the driver gas should be a low molecular weight gas at high temperature and the driven gas should be a high molecular weight gas at low temperature. This is a very, very important fact which is to be kept by designers as well as users of shock tubes. So, what we are saying is that we talked about a pressure difference across the diaphragm before it had ruptured. We are talking about that pressure as the diaphragm pressure ratio. So, you have say the driver section pressure here and the driven section pressure here. Sorry, this should be driver. Let us correct it. We will rewrite this. So, this is driver and this is driven. So, the pressure ratio between driver and driven, that gives you the diaphragm pressure ratio. So, this if it is a fixed value based on what has been chosen by the designers, under that constraint how do you maximize the incident shock strength? So, the incident shock strength will change based on what choices you make of the driver gas and the driven gas and also at what temperatures you maintain them. And why is it important for you to change the incident shock strength? Then you end up changing the Mach number of that shock, and that is how you can use that shock tube for creating shocks of different strengths and different Mach numbers effectively. So, this is a very, very important application perspective. And then we have a guideline that you have to have a high temperature lighter gas in the driver section and low temperature heavier gas in the driven section. In that case, the incident shock strength will be high. And for this reason, many shock tubes use a lighter gas like hydrogen or helium in the driver section, and they are even preheated either by electrical means in arc driven shock tubes. So, you have an electrical arc heating up the gas, or by chemical combustion in combustion driven shock tubes. Okay. So, if you raise the temperature of the gas before you run the shock tube by rupturing the diaphragm, this is what is called as a preheating. So, in this lecture we discussed about some preliminary concepts of hypersonic flow. Further, we had an introductory discussion of shock tube, which is a very important apparatus for studying shocks over a range of Mach numbers, and that spans over supersonic to hypersonic range. Thank you.